Well, hi, good morning. Thanks so much for joining me here in my shop on the 18th of December. And today is capacitor day for this radio. I'm going to be changing out all these capacitors here, all the paper capacitors. But before I do that, I wanted to do a test or two on the radio to try to better judge not so much its performance, but the effect of having these bad capacitors in the radio. Now there's one in particular that there's a very objective way of testing its effectiveness, and that's the grid blocking capacitor, if I can call it that, for the output tube. And this is the capacitor through which the signal from the output tube plate circuit is passed on to the well, I got that a little backwards, didn't I? let me just back up a little bit. This is a grid of the output tube, has a capacitor through which the signal reaches the grid of the output tube from the previous tube plate, which has some voltage on it, and we don't want any of that positive voltage to get onto the grid of the output tube. So it's a bit of a silent killer in a radio like this. And I think it'd just be interesting to look and see what's happening to the grid potential. So I'm going to set up for that. Just have to get a voltmeter ready, identify which capacitor it is, and that sort of stuff. Away we go. Okay, so this is the output tube socket here, and one of these capacitors right in this area is bound to be the one in question. Bet you it's this one. I can see the size of it there. Let me just peek at the schematic quickly, and it should be a 0.01. So I see a 0.02 here. Bet you this is it here then. That looks, maybe this one. Okay, let's see. Should be on pin 7. So counting here. 8, 7. That's 7. That didn't work out. Now it could also be because there's 2 pins on this tube that connect to the grid. So we could find it on pin number 1. Wow, pin number 1 is completely open on this tube. Did I count this wrong? You know, I think I did. I think I counted this wrong. This is 7 pins on this tube, Jim, not 8. Okay, so pin 7 is going to be this guy. It's this one. It's this capacitor right here. Okay, I don't want to rotate it. Can't quite see the size of it, but that's got to be it. Any other hints about that? So there's a resistor going to ground here from that same pin. That would be tricky here, a 470K resistor. And sure enough, purple, yellow, purple. Purple, yellow, purple. Purple, yellow, purple. That would be 470K. Why is this not working out? Did I not get enough sleep last night? What happened here? Okay, I'm going to do this is the idiot. I have to pull out the idiot guide once in a while here. Just because. I guess that's because sometimes I'm an idiot here. Let's go. 40, come on. Okay, so I read it the wrong direction. That's what I'm doing. So if I look a little further down in the shadow here, it's yellow, purple, yellow. There we go, 47, 470K. Okay, that all adds up. And this is certainly the grid. And this is certainly the capacitor. So I want to measure the voltage to what? Not to the chassis. I don't want to measure it to this negative line here on the schematic. At the bottom of these capacitors is the place where I can find it for certain. Another place is the far side of the 470 is connected to it. So I could just go from this wire, which you may not be able to see because of the thing there. There's a wire right here on the other side of this resistor that's connected to ground. Just measure across that resistor. That's pretty much what it amounts to. That's the resistor there. Yeah, just across the resistor. Give me the grid potential. Now grids are high impedance, so you need to use a high impedance meter, but everybody has a high impedance meter these days. And I'm going to use a vacuum tube voltmeter to do it, because I like the old equipment. Why is that? Because I'm old too. Oh, I hate to admit that, but yeah. Okay, radio is switched on. Apply some power. There we go. All is normal. I'm going to give it the full treatment here. So by throwing this switch up, power goes straight to the radio. It doesn't go through these dim light bulbs I have hooked up there. Yeah. Connecting the ground lead into the middle of a radio that's turned on is not the wisest idea either. So I'm going to turn it off. I think as you're waving this around while you're doing it. Yeah, lots of false starts here this morning. Okay, we're going to set this. I'm going to guess it's going to go negative. I'm going to set this to 15 volts, full scale, negative. Does that really make sense? So really what's going on with this tube is the cathode is being pushed positive. So the grid itself is actually running around ground potential. So I really don't know which way it's going to go. It really shouldn't go anywhere, I guess. I guess that would be the right answer. We should find kind of 0 DC volts on it. Let's switch it on again. Okay, so you notice the dim bulbs didn't come on this time? That's because it's already charged up. Okay, we're feeding it only 105. We'll give it just a little more. Just a little more. Okay, make sure it's working. Okay, here we go. What do we get? That's my hand on the meter. Watching that meter. You see it's got a positive voltage on it. Okay, we'll put this here. So on the 15 volt scale, that would be almost 3 volts positive. Now, positive, it's positive to the B minus. The cathode should still be a little more positive yet. 6.5 volts is what it's supposed to be. So now we'll touch on the cathode. The cathode is number 2, pin number 2. Or same thing would be the positive side of this capacitor I put in. Positive side of the little tiny capacitor. Well, I've got that so covered up here I can't get at it. So I'll go up on the pin. And we're looking for 6.5 volts positive if all is normal. Okay, so I'm reading there on the 15 volt scale. I'm reading 8 volts. 8 volts positive. So we have the cathode is 8 volts positive. A little higher than what it's supposed to be. So that's a suggestion that this resistor, the cathode resistor, has gone high, which is very, very common. So we'll look into that after the radio's switched off. It's supposed to be 220 ohms. I'll bet you it's 260 or 280 or something like that. Having the grid bias go a little further negative is not so bad. I mean, between the two of them, because they're both elevated. Oops, they're both elevated. The voltage between them is roughly the 6 volts that's supposed to be there. You don't really want to measure it with this meter directly. Excuse me. So, okay, let's check that resistor. Turn everything off. I'll take this out of here. Must be my house has become dry. It's causing me to have a little cough. So, hey, how's the COVID thing where you live? Here in Canada, I think generally across Canada, everyone's gotten quite nervous and quite upset because Christmas is going down the drain. I don't think there's any two ways to look at it. It's just going down the drain here. Some parts of Canada are experiencing the worst COVID outbreaks they've had yet. For this whole COVID thing, right now the worst outbreaks are happening in some very localized regions of Canada. But we're all next. I mean, it's pretty clear from all the information that the Omicron is going to get us. And my wife and I were out yesterday shopping. I said to her, let's go do our grocery shopping now. We'll try to shop enough that we can stay home for the next 4 weeks or so. I don't think we achieved that, but that was kind of the goal. So we don't have to go out again. So I'm going out. I'm very, very concerned that, you know, the basic rule is that guy who's close to you, that's the guy who's going to give it to you. And I'm going through a store, Canadian Tire store here in Canada. These are really very much very well-known stores, and that big store, big new store here in Aurelia, huge in fact, packed with products that they want to sell. So the aisles have become narrowed. So I'm going down the aisle with my shopping cart. There's a guy and a wife coming towards me. What is wrong with people? He's wearing the mask, but it's dropped below his nose, so his nose is sticking out. I'm saying to myself, okay, that's the guy who's going to make me sick. You better try to maximize my avoidance of him. I decide to continue down the aisle. And what I'm going to do is, just as I go by him, I'm just going to look away. I'm going to be exhaling. I'm serious. I do these things. And I won't inhale till I get to the far side. Traveling down, he looks at me, I look at him. I can tell he's smiling. And in a friendly way, as I go by, he leans over to me and goes, "Pretty crowded in here, eh?" And he's just trying to be friendly. He's just trying to be kind. And I'm thinking, what are you doing? You're injecting me with Omicron. Get away from me. So, you know what? I got a sore throat tomorrow. I'll know who it was. Sore throat. I think that's the indicator for Omicron. The early indicator. Okay, enough of that stuff. Now, where is this resistor? 220 is going to be a red. Red. Where are you? There. There's a red, yellow there, but that's not it. There's another one down there with red. That also looks like red, yellow. That's not going to be it. Well, it's got to be off the cathode here. Where are you? Oh, there it is, totally hidden from view. Way back in there. It's a fairly large one. Like, it looks like a half watt as opposed to a quarter watt. Doesn't say on here what it is, but that's probably, I mean, it's connected to the right place. Okay, just making absolutely sure I'm testing the right thing. Check the meter. Check the meter. Okay. From here, down to here. 400. So that's supposed to be 220. You know, if it was 250, I wouldn't think much of it. 400. Wow. That's gone way high. So now we have a little bit of a decision to make. Should I just leave it there? So it's double what it should be. It's not going to create double the voltage because it's having the effect of slowing or reducing the current flow through the tube too. Yeah, 220 right here. Well, I'll tell you what, let's take a look in the tube manual and see what it recommends. Of course, the people who designed and engineered this thing would know better. But let's just get some information here. We'll see what the book says about a 50B5. 50B5. Uh-oh. There's not much information here on it. Because of its high power sensitivity at plate and screen grid voltages available in AC/DC receivers, it is capable of providing a relatively high power output. So what they're saying is the 50B5 can work well with low voltages. You only have low voltages in a radio like this. 100 110 volts. According to that, it's going to tell me another tube to look at. The tube requires miniature 7th mm mounted in place. For basing arrangement, 50B5 identical with 50C5. It doesn't actually say much about it. A lot of these tubes, the book will recommend what the cathode bias resistor should be. Let's just look under 50C5. B5, C5, how different can they be? And it doesn't say. Okay, this did not help at all. So all we got to go on is what the designers of the radio had suggested, which I'm sure is fine. And I could do a little more research, but just flogging an unnecessary horse. An unnecessary flogging for a horse. So I will change it out. We'll put in the 220. You can always see what's going to happen. This capacitor's got to be changed too, in order to kind of clean that whole situation up. Why don't I do this? Leave it like it is. Change the capacitor. See what happens to the grid voltage if it returns to what I believe it should be, 0 relative to B minus, and loses its little positive voltage. You can also check the capacitor to see how leaky it is. Now that sounds like a way to go. Okay, first step is cut the existing one out. That looks terrible. That has the look of a melted capacitor. Huh. Sitting like it would be sitting. Well, it would have been sitting like this, which means it was sitting like this. You kind of think melted wax would kind of drip off the bottom. Looks like wax has come out of it here, or off of the end of it. I don't know. Not a very good looking one. In fact, it's pretty ugly looking. Okay, so here's my capacitor checker here. Put it on. So these old capacitor checkers, if you're not my age, they work a little different than the newer ones. Capacitors were, the demands on the capacitors were different. It had to withstand some voltage. In today's world, capacitors, they're barely tickled. Okay, so the way this works, throw this spring-loaded switch and it'll apply the voltage. During the current flow, it charges up the capacitor. The eye will close. And when the current finally comes to an end, the eye will drift back open. If it opens up like you see it now, at the bottom here, you can see the pi now. That means there's no current leakage. Anybody want to put a bet on this one? My bet is it'll close and it won't open. Here we go. That's 50 volts I'm putting on it. Okay, if you're sharp-eyed, you can read the 25 here. It's actually 50. I've measured it. And the capacitor shows that it's leaking badly. Now, I tested so many of these capacitors. I have a good qualitative understanding of what to expect with that test. For sure, a new capacitor, that eye would pop right open. The sort of half-ill capacitor, a lot of them coming out of these old radios, the eye is about halfway, which I think is still indicating it may be bad. This is in a very sensitive location. A small leakage of current that changed that grid potential. Okay, and shrink, in effect, shrink the bias on it. That's how I would interpret that. Interestingly enough, it's kind of compensation for the resistor, which has gone high. It's kind of an unusual situation. So I'll stick a new one in there. We'll run the radio and we'll measure it. Oh, let's just check the size of this to make sure it is what it's supposed to be. Yeah, 0.01. That's exactly right. Hey, everything's adding up this morning. was watching a TV show this morning. Oh, by the way, if you're British, if you're in England, let me thank you. Let me thank you for paying taxes to keep something called the BBC going. BBC is a wonderful thing, wonderful for the world. It's been wonderful for me all my life, but now on my television set I get to watch BBC TV of various sorts. I watch BBC Earth a lot and other shows like that, so thank you very much for supporting that service. It's fantastic. I was watching a show, they were talking about primates, of which we are a member, and they were talking about the difference between primates and other animals, and they're talking about, of course, hands being a big thing. Hands are a big thing. But you know, I notice, because I see a lot of squirrels at our house, squirrels have hands, and they grab things. But here's the difference between, this is why a squirrel isn't in here fixing this radio right now. When squirrels operate their hands, and other animals with hands, not primates, but other animals, their hands are operated in a symmetrical fashion. So if you watch a squirrel pick something up, it goes like this, and then it eats it, basically eats a nut, right? It'll hold it. You can see it's holding it, but it's always symmetrical. What sets us apart and other primates apart is the independent operation of our two hands. One hand can be doing one thing and the other hand can be doing something else. And that is a big, big part of what separates us from the general animal kingdom, or at least what separates primates. Primates out. Just fascinating watching this show. So let me thank you again for the BBC. You know, when I was a kid, because I was a shortwave guy, I listened to the BBC a lot, BBC radio. And you know, in Canada we have something very similar. We have the CBC. It's also supported by tax money. CBC radio is. CBC television, I don't know to what degree, but it was originally non-commercial when I was a kid, and then it became commercial. So at some point one of the governments said, well, make them pay for themselves with advertising. So unfortunately we watch BBC TV. It's just like or CBC TV. It's kind of like any other commercial TV channel. There's nothing particularly special about it. So I'm going to guess some people in Britain take it all for granted, and probably even complain. Why do we, you know, people who may not watch or listen to this, I don't know, can you not watch BBC? Do they have commercial TV? I think they might, but it's so easy for us to forget the value of things we already have and consider the value of things we don't have. And there we go. Yeah. Or in the words of the famous song, you don't know what you got till it's gone. So you got something great there. You really do. If you're American, you're on the other extreme. Yeah, you've got NPR, but that's not really government supported. That's just not so commercial, or not commercial. But you don't have this thing. Part of what that does, by the way, I know here in Canada, the CBC, like it or not, watch it or not, listen to it or not, it provides a foundation from which things can be measured. So if you are watching the news in Canada, it doesn't matter whether it's commercial news or the CBC, the news stories are basically the same. Basically, they see the world the same way. There's none of this thing that's going on in the United States where the news media has been divided into two groups. It's a terrible thing that's happened. And, you know, we'd be better off all believing well, maybe it's not true what I was going to say. All believing the same thing, even if the same thing isn't true. No, I don't think that's the case. I think that's ultimately the extreme danger. Okay, so the capacitor's in, and I'm talking too much. Let me turn on the radio. And now we want to look for that positive voltage we saw before. I've turned it on, and I have not got this set up. Turn it off. It's a big bare clip lead. It's not really the best thing. I could probably do something a lot better than that. Okay, and turn it on. All is good. Last time we saw a small voltage on the meter, just under 3 volts in fact. That being the case, I'm going to switch this to 5 volts. So it's 5 volts, 3 volts up around here somewhere. Did this make a difference? Is the radio working? Yep. Did it make any difference? Look at that. There's nothing there now. So that certainly made a difference. So that will have increased the negative bias out to a somewhat crazy amount. Let me just check now what, well, I can't. The cathode would still read the same amount. That's good though. Clearly that capacitor was causing the death throws in this radio. Now because of the way it's biased, it's not quite so bad. If the radio was utilizing a grid bias technique where they change the voltage of the grid rather than change the voltage of the cathode, that would really be badly interfered with by this kind of situation, which is oh so common in these old radios. I mean, all these capacitors in here are going to be leaking to some degree, but many of them, it's just immaterial that it's leaking. It's just not an important thing. Maybe there's some others that are in the grid blocking business I can find in here. Not sure there are. Okay, any change in the sound? Well, not really. No, you wouldn't probably notice a change. Probably a small change in the volume maybe. But at this point, because we've now increased the effective negative bias on the tube quiescent current or through current should be less. More in line with what it should be. In fact, because of the high cathode resistor, it's probably much less than what it's really intended to be. So the result of that is you have a range within which you can operate the tube without distortion or with minimal distortion. And you want to kind of set the bias so the tube's operation comes into the middle of that range. So with this radio right now, it's not in the middle. Forget whether this is which way is positive or negative. It's just out. So what that means is the signal comes along, it's going to hit this limit. Whereas before, when it's done right, it's got all this range. So what would it sound like? Distortion, harmonic distortion, loss of volume, crappy sound is what it would sound like. But we're not going to try to test for that. It's time to do the resistor. Okay, power off, Jim. Okay, I'm going to put a new 220 resistor in there. Okay, we're ready for another test. So rather than put a 220 in, I put a 250 in because I have one that's the right wattage. So but a little bit bigger is a little bit better in a sense. A little bit smaller would be a mistake, considering it was running with 400 and something. Okay, so what we're looking for now, again, is the cathode voltage to be, let's see what it really says here, 5.8 volts. Very precisely, 5.8 volts. Well, let's see what we got. So that's again to the B minus. This is on the B minus here. All looks safe. Plug it back in. Charge up. I guess, we could have gone a lot farther with testing this. I could have been feeding in a signal into the phono input. We could be listening to it. I could drive up its level, see about the clipping, thing, all that kind of stuff I could have done, but I didn't. This is pretty quiet. There it comes. A bit of dirt in the volume control. Sounds fine. What is the voltage? Okay, so we should see it right here. Got my hand out from in front of the meter. So So I don't want to steady my hand like this. I don't want to put my hand on here and steady it. So that's here. This is a better idea. You stand over here and look at that meter. I will stick this lead on the spot. Now we're on the 15 ohm scale now, so we're looking at it having it come up in this range right around here. Look at that, 5.8. That's what my meter actually says, 5.8. And what it's called for? 5.8, just like magic, like magic. I got the wrong size resistor in there, but only by a little bit. A little bit. And there's sort of a compensatory action in the tube, a little bit anyway. So it's like, okay. Very good. So we solved the problem, got rid of a bad capacitor, and fixed the cathode bias on the output tube. Very good. Okay, gotta think of something next. What will come next? Okay, so we just looked back at the biasing on the previous tubes here. We come to the detector tube, which is a two-part tube. The detector thing is one thing, and the preamp is another part of this tube right here. So there's a grid in there. It has to be biased. And the way this one is done, and by the way, everything I say, grain of salt taken with it. So this one is self-biased. It has this great big resistor here, 10 megohms. No sign of any other form of biasing. You just wait a second. Take a look at the cathode. Cathode is connected straight to B minus, so there's no other form of biasing. So you can't have the grid sitting at 0 volts relative to the cathode, or you're going to be down here the whole time. That's just not going to work. So, so what happens in this tube is it self-biases. And so when you first think about it, first turn on the radio, there's no voltage on the grid at all. Then there's electrons shooting through the tube, or let's put it this way, there's an electronic pressure inside the evacuated part of the tube. And that pressure causes the crowd of electrons in there, some of them are going to get on the grid. Shame on them, but they will. And the grid, as it collects electrons, will become more and more negative. Once the and then there's a signal on the grid which is causing the voltage to go up and down. So you could think of it almost this way: with the radio off but on somehow, you have a signal on the grid, and then you sort of activate the tube. I mean, this can't happen, this is just a thought experiment, and the grid starts going negative because it's picking up electrons. It goes negative particularly because it's going positive, because the signal reaching the grid is pushing it positive. As soon as it goes positive, all those electrons start jumping on board. It goes down negative, they can't get off. They cannot get off. The grid is not hot, so it can't emit them, so it holds on to them. So slowly the grid becomes more and more negative. And so long as this thing dips into the positive zone, it will pick up some more charge and go a little more negative. Now, it can only go so negative because that 10 megohm resistor is allowing a few of them out the back door all the time. So the charge, the amount, the coulomb charge on there is going down at the same time it's going up. But at some point, the grid with the signal on it will not go into the positive zone, or just nick the positive zone, pick up a little more charge, and it will just hang around down here, essentially negative, and pretty much in the zone for operation. That's called self-biasing. Not much can go wrong with that. This 10 megohm resistor is bound to be 10 megohms. What if it's floated up to 15? I don't think that'll make much of a difference. I really don't. If it were open, there'd be no way for charge to get off the grid, and maybe in the long run, because it's being slammed by electrons. The odd electron is piling right into it. It's going to pick up more negative charge. So that's how this one's biased. It's self-biasing. I guess one issue would be this capacitor here. The other part about that is trying to measure the grid voltage is pretty much impossible. With this 10 megohm resistor here, I bring up my meter and stick it on there to make a measurement. Well, my meter is I think it's a 1 or 10. 10 or 1? I don't know. I can't remember. it's a high impedance, but it's not high compared to this. And so it will start bleeding off the charge faster than would happen if the meter wasn't on it. So the meter will influence the circuit an awful lot. You get a false reading. So this capacitor here is trying to block some DC from getting over here. The DC is coming from this circuit. This is the output of the detector, and it's designed to rectify the signal coming out of the IF. And they've arranged it purposefully so that wire will go negative. They could do this differently and the wire would go positive. It doesn't really matter in itself, but the negative voltage is very useful. So they arrange it to go negative, and then they can apply that negative voltage back here for more biasing, but we'll get to that in a minute. So if this resistor is leaky, which it certainly is, what would happen? Some small amount of negative charge would make it through here. This is a small voltage here, 5 volts, maybe not even that. Resistors here and the like, but nevertheless some small amount would make it through. And as you vary the volume control, you would vary that small amount. One effect of that is a scratchy volume control that you cannot clean away. Clean it all you like, and every time you do because there's DC going through it, and that's just the result of having DC go through that control. Is this thing scratchy? I wouldn't say so. I've heard some that are, you know, really scratchy, and it's not dirt in the control. So it's probably leaking a little bit, but not enough to make a big difference because there's not much pressure pushing and all that kind of stuff. So probably not really a problem in here. It will eventually change this. Now if we consider the biasing on these other tubes, so they're getting their biasing from this arrangement with the detector, which is producing a negative voltage of a few volts. Depends how strong the signal is in the radio. The stronger the signal, the more voltage getting rectified, the higher this DC, this negative DC. So these tubes are designed to take advantage of this. Their grids, if you vary the grid bias up and down, you'll vary the amplification of these tubes, the mu of these tubes. So more bias on the grid means less amplification. So we use this feature to cause the tubes here to be less powerful. I could put it that way, I guess. Less amplification. And it occurs when there's a very strong signal. It's just a little bit counterintuitive that you can use the signal itself to cut itself back, but that's essentially what's going on. This stuff is all figured out, of course, and arranged so that ultimately it hardly matters what level of signal comes through here. The volume in the speaker will be essentially the same. The big benefit of that is as you tune the radio from station to station, the weak station, strong station, the volume coming out of the speaker stays relatively the same. Otherwise you got to hold on to the volume control. So that's automatic volume control, AVC, voltage. You can have some funny things happen with the AVC. If things aren't right in the AVC, you can get something called motor boating, where essentially the sensitivity of the radio is going up and down like this, and maybe going fast up and down. It may sound like pop, 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 and some funny sounds can come out of a radio from difficulties with the AVC circuit. Of course, those things are all thought through by the designers. There's no magic here. This is all well-known stuff. What could potentially be wrong in that circuit, I'm not saying there is anything wrong, is this important capacitor here, which is trying to, see, it's on the other side of this great big resistor. So you have a little voltage here, pushing charge through this resistor, trying to raise this wire and the grids up to the same voltage over here. Doesn't take a lot of charge, a very small amount of charge come through here will vary this voltage quite a bit. You can afford to put a huge resistor there. But if this capacitor is leaky, that small charge is going to bleed off back to the B minus, and you're not going to have the AVC you're supposed to have. It's going to be retarded by this leaky capacitor. Maybe that's the appropriate word there. If you remove this capacitor, you're going to get I'm sure you're going to get all kinds of weirdness going on. So you don't want that to happen. A secondary benefit of this capacitor is if there's any audio that's come through, because this is actually the audio circuit back here. It's the audio with that DC stuck on top of it. See, basically you're splitting the audio and sending it this way using a capacitor to stop the DC. This way you don't want the audio. So another purpose of this guy is to just shut off the audio. Now if you got some audio signal on these RF tubes, I'm not exactly sure what would happen, but it wouldn't be good. And again, you can get probably weird effects, maybe even some feedback right through the radio. So now you get a squealer going, or a squawker, or something like that. So what is the next capacitor that we should be suspicious of in this radio? Who would be the bad guy? There's still one way over here. That's this one. You can see peeking out right here. So that guy is hooked up to the plate and runs back to the cathode. So it's connected. It's not connected to B minus. It's connected right to the cathode. So it's kind of shorting out the plate and the cathode, which doesn't sound like a good idea, but it's sized in such a way, and things are arranged in such a way that really what it does is it kills any RF that might have made it all the way through here accidentally. Not supposed to be any RF out here, but there could be, and just get rid of it and make sure it doesn't go through the transformer here and head for the speaker. Not that you're going to hear RF coming out of a speaker, but it's just you don't want it there, so you can get rid of it. So that's what that guy's doing. Now if he's not working well, I don't know. If it's leaky, well, that's kind of interesting now. I never thought about this guy. If he's leaky, he's got the B plus on one side. You can leak B plus right onto the cathode. Now we measured the cathode at the perfect voltage, and there is pressure on this capacitor, unlike the one over here. And over here, this one's got pressure on it, about 110 volts of pressure. Pressure is a better term. You know, if you're going to be thinking about these things, you should use the term pressure instead of voltage. That is how it was viewed 100 years ago. The term voltage came a little later, to show some respect to Mr. Volta. Voltage doesn't mean anything in itself, but pressure, we all know what pressure is. Pressure is what it is. So there's some pressure on here, some charge leaking back. Could be the case that because you've got a small resistor here, 220 ohms, it can't leak enough charge to affect the potential of this, of the cathode. It's probably the case. If this were really bad, like shorted, whoa. Well, I don't know what all that would do. It would certainly stop the radio from operating. So it could be open in the sense that its capacitance may have fallen off. In that case, I guess the RF would continue to be present here, and the effect of that, I'm not sure. You just don't want it there, I think. Okay, so this guy's a good target to change. Don't think it would see any effect. I already measured this 5.8 voltage and got 5.8. That sort of suggests that this capacitor is really not leaking enough to cause a problem. But he's going to go anyway, for sure. Who else is in here that might be causing a serious problem? So some of these capacitors are tubular paper type capacitors. There's the ones that cause the problems. They just don't have the life. But capacitors that are much smaller and are ceramic capacitors, like it shows here, not likely to cause a problem. In my experience, I've changed very, very few of these. Very few. So probably some of these capacitors, like maybe this one, M47. M means mica. So mica, again, mica and ceramic, very reliable capacitor. So I wouldn't even think about this one for a radio like this. Wouldn't even consider it. So stop considering it. Got another one up here. That's another mica one. So really, it's these T ones, tubular capacitors that we should really be looking at. Okay, so is there another T? You looked at that one. That's an M. That's an M. There's a T. We did that one. That's the first. That's the one we did. Sounds like there's a lot more of them in there. 1, 2, 3, 4, 5, 6. Still 6 in there. So here's one here. So one of them is this one. This is the safety capacitor. I shouldn't really use that term. So what this guy's really all about is why don't you just get rid of it? It's the connection to the chassis. This is only part of the story, of course. A lot of these things are doing double and triple duty. But one of the jobs of this capacitor is to take the signals that are inevitably being picked up by this chassis, which is basically a big stupid antenna. Big stupid antenna, and if you're not careful, the big stupid antenna, if you just connected, if you didn't do anything with it, if you left it unconnected, so it's a stupid antenna, it's not even connected to the radio, it just happens to be in proximity. A little hard to believe that the chassis could just be in proximity with all that stuff that's in it, but that's the state of affairs. That proximity means you're bringing these stupid signals, noise and crap and all kinds of stuff that's being picked up in this chassis, and allowing it to radiate back into the radio. And another possibility is the radio itself is generating signals inside it. The output of the IF can be strong, the local oscillator can be strong. Those things can be, because they're at RF frequencies, they can find their way into the stupid antenna and then find their way out of the stupid antenna back into some part of the sensitive part of the circuit, and you get kind of a feedback, and that's going to sound like screeches and howls and who knows what. So we don't have any of that in this radio. We can be pretty sure this guy is doing enough to quell that kind of problem. The other thing is it's involved with the very, very front end, the antenna and the tuning gang, and I have some trouble explaining the ins and outs of that. I'm not well enough aware to sit here and talk about it. So that's the deal. There's only really no other capacitor to be too worried about. Well, maybe this one. We'll go after this guy. This is the volume control capacitor, which could potentially leak a little bit of extra negative voltage onto the grid, but we can't measure it effectively, so we don't really know what's going on here. We'd have to just take a wild guess. Okay, if it's leaking enough, you'd really have the AVC voltage showing up over here, and then that would vary as you move the volume control. You'd have some weird thing going on. I don't know what it would be. Weird stuff. We'll go after that one next. The capacitor on the volume control. Okay, well, just keep the video rolling here. Capacitor on the, let's turn it off before I stick my finger in there. So where's the volume control? There it is. There's the 3 terminals. So this is the center terminal. There's the capacitor right there. That's the guy we want to change next. It says here that it's 1. Can't be a 1. Must be a 0.1, 0.01. I just can't see the point in the 0. That's the guy we're going to do. I'll keep the video rolling. I'll cut him out and we'll test him. Could talk a little bit about the now I'm going to lose track. I'm a little worried. Have you ever realized why when a surgeon's working on a patient and he needs the next tool, hand me the screwdriver, he just sticks his hand out. He keeps looking at the surgery. He sticks his hand out, hand me the screwdriver, and the nurse puts the screw, or whoever puts a screwdriver in his hand exactly the way he needs it, right, pointing the right way. Back it comes and he screwdrivers the patient. The reason is, if he takes his eyes off that patient, when he looks back, he won't know what he was doing. And this happens to me all the time doing this work, and it would happen to anybody, I think. You're looking at this terminal, you cut the capacitor off, and walk away, fool around, drink some coffee. Even just a fraction of a second is enough. When you look back, where'd that come from again? So to prevent that problem, what I do, I just grab a clip lead and I clip it on the terminal in question. Because I am going to go drink some coffee when I cut this out after I test it. And when I come back, I won't make a mistake. And if you think you won't make a mistake, you're going to make a mistake. That's a mistake. That's the mistake right there. You must assume you're going to get it wrong. But I don't have a nurse here. You may need a psychiatric nurse. 0.01. There it is. Looking very rough. Looks like it doesn't look well wax sealed anymore. When I started this morning, I thought, well, what I'll do is I'll just talk a little bit and then I'll change all the capacitors and we'll just turn the radio on and see what happens. But look what I'm doing. I'm going one by one, analyzing them all. I think that's fun. If you haven't figured it out yet, I'm always looking for the fun way of doing this. Occasionally there is no fun way, but often there is a fun way of doing this kind of work. And I keep the fun level high. As I said to my buddy yesterday, never be childish, always be childlike. Okay, let's see what happens here. Watching the eye. How leaky are you? Ah, you're a piece of crap. It's worse than the other one. It's worse than the last capacitor. You probably can't see it, but I can certainly see it. The eye's actually overlapping there. This is a very leaky capacitor. And now, for my own edification, I'm going to test it on another tester. So, look at this guy. I try not to let my other test equipment see this, because if they see it, they'll just feel so terrible about themselves, the old test equipment in here. Because this is a wonderful piece of inexpensive test gear. Shh, I shouldn't have even said that. Oh my God, some of my equipment has ears. Here we go. What do you say? You say, well, V lost 12%. The capacitance measures at 37 nanofarads. Now, what I've sort of determined here in my own experience is when the capacitor is in good shape, these instruments work. When the capacitor is leaky, these instruments, they start telling you lies. So you really need to think about that. Let's see. Let's repeat the experiment. Do we get consistent? Yes, we get consistent results. So I know V loss, that's a very high number there. That's probably reflective of the leak through the capacitor. I don't know what the official meaning of V loss is because I'm just too old. I went to school in the 70s. What can I tell you? 36 nanofarads would be the same as 0.03 microfarads. 0.03, but it's a 0.01. How did it get to have more capacitance? Well, it hasn't. It's the meter is thrown off because of the leak. That's my understanding of that. So, doubt everything. Doubt everything. That's certainly, after all these years walking on the earth, that's what I tell you. Doubt it all. Okay, so we'll put a new capacitor in there, and we just can't really directly test the result of doing this. But I think we can be reassured it's an improvement of some sort. And now it's coffee break time here. Okay, got the capacitor in. So that's the one off the volume control. One thing I didn't mention was if this guy's capacitance has gone low, it's not what it's supposed to be, maybe some of the volume or the signal coming through here will not make it, basically. You end up with a quieter radio. Okay. But there seems to be a lot of volume in this radio anyway. I think we're ready for another test. Here we go. Okay, dim bulbs look good. moment. So this latest, while we're waiting here, latest COVID wave coming through Canada. The lucky thing is, before this wave of Delta and now Omicron are coming through, our hospital systems had the pressure had come down on them quite a bit. So we had a bit of capacity there, and maybe some of the pressure came off the hospital people who had been, as we all know, really stressed out about this whole situation. So there's been a fair bit of capacity, and what's happening here in Canada is the capacity is coming right up. In some places it's hit the top, and patients have to be sent quite a distance from where they live to find a hospital that's got some capacity, like a long distance. So we've consumed this capacity in some places. Other places the capacity is going like this. My understanding, from watching the news and that, the American situation is very different. The Americans never brought it down after September, after the last wave, and their hospitals have been right here. Again, it's a big country, lots of things going on. I'm sure it varies a bit from place to place, but generally speaking, it's here, and it's going up from here. So the situation in the United States, I believe, is going to become a super duper panic in just a matter of a week or two. Because they're a little behind us. For some reason, this Omicron thing has penetrated Canada a little bit quicker than it's penetrated the United States. But my gosh, vaccination rates here very high, 85% of 5 and over, something like that. I probably don't have that number quite right, but it's right up there. And people are getting vaccinated right now, and the third vaccination, the booster shot thing, is happening. But unfortunately, you can only serve that stuff out so fast. And I would like to spank some of the governments here in Canada, the provincial governments, only really concerned about my own here in Ontario, for having not set everything up ahead of time. So when this wave came through, everything would be ready to go. Instead, there's a big scramble going on. There shouldn't be any scramble. Now, why is there a piece of wire? Oh, it's not a piece of wire. Okay, it's just a piece of dust hanging on a spider web. Hey, let's turn it up. There we are. I might have more volume. Hard to say. Didn't do anything objective to find out. How about picking something up? Well, the radio's up on its side right now. I can't really aim the... I could. Let me take my break off there. There we are. Very good. Okay, I think that's it for today. I'm a little worn out. I got other things I'd like to do. So that's pretty good progress anyway. That was lots of fun. I had lots of fun doing that. Hope you enjoyed that. And I hope you'll join me tomorrow. I continue on with knocking out a few more capacitors, and we're approaching the point of tuning up and aligning the radio. Great. Thanks a lot for watching.